recording.
All right, guys, this is Bitcoin, a peer-to-peer electronic cash system. Again, my name is Edu Medeiros, and this is our agenda for this and the next session. So, the last session we covered uh, the economy with digital transactions. I will go into this again just briefly, just to set us our minds again. We talked about the Bitcoin data structures that we call transactions, and we talked about the Bitcoin programming language that is embedded in the system that makes money programmable. And today, my plan is to give at least a one-on-one introduction of the public key cryptography that's used in the system. Are we good? Because I'm hearing a lot of noise here.
Yeah, we are
Amos?
good. We are good.
Okay, so all right. So the problem we are trying to fix is to build a digital transaction system, which is just a message uh, sending and receiving digital messages. But we want to do this without a single point of failure in that in our case is banking or credit card processing company or something. And for this, we defined what the transaction will be in the system, and the transactions are the messages people send to each other in this system, and it is this data structure. We saw it has a version number, a log time thing. It has a vector of inputs, and those vector of inputs they point to a previous transaction that you are trying to spend. It actually points to one output on a previous transaction that we are trying to expand. There is this sequence number we are not going into in these talks, and we have this script sig field. And one of the things that we usually put in this script sig is a signature, is a digital signature that authorizes me to spend some value in the system. And we are going to uh, dive deeper today on the mathematics behind these numbers here and how those things are verified, right? We also talked about scripts. And the important thing here is to understand there is a locking script that someone puts in the output of transactions. And this locking script defines who's the owner of the value defined by that output, right? And anyone who is trying to spend those funds, who believes he's the faithful owner of those funds, is uh, it he or she has to provide an unlocking script, which is put into a later transaction input. And most of the time, this unlocking script will have a signature, and will the locking script will ask to check for if the signature is valid somehow. And today I want to explain, or at least give some hints about what does it mean to have a valid signature, and how do we create signatures, and how do we verify signatures. This is the basic operations we have to be able to perform to use this system. And Bitcoin in specific is based on elliptic curve cryptography, and which is a specific kind of public key system, cryptographic system, which is not the only way to do these things, but it's pretty convenient to do this because we can use pretty small keys and achieve quite high security levels on the system, and so it's quite convenient to do so. And the basic idea of this kind of cryptography is to be able to construct what I'm going to call one-way functions, which are functions that are given an input, it's easy or it's computationally cheap to produce an output, but given the output of the function, it is extremely computationally expensive to compute the input that creates that output, that specific output on any function, right? And on oops, on the what I will show you here is one way of creating this first part here, the the function that takes private keys and create public keys, and it's based on what will be called the discrete logarithm problem. I hope you will understand what this thing mean, right? But on on Bitcoin, we also use hashing functions, which has kind of the same property. I'm not going to explain how those things are built here. They are pretty standard, actually. They are not hard to understand. They are quite clever ways to mix bits in a computer. It's interesting, but it's not that interesting. You can just go and see how they are built. And all right. So people usually start explaining what a finite field is, and then what an elliptic curve is, and then elliptic curves using finite fields, and then explaining how to use this to create signatures. I will take the inverse path because, come on, you guys are computer science guys, so you will understand the algorithm first, and you can reason using primitives just like a library, right? And then after that, after we understand what we are trying to achieve, we can go deeper and open the black box to see how the primitives that the some kind of library has to provide me to be able to perform these algorithms. So the two basic operations that I want to define here. The first one is signing. How do I take piece, a message, a piece of information, and produce a number that I will call a digital signature that can be later verified by someone else, right? So this is the first thing. So I will start considering that there is uh, something that I will call G. G is a constant defined by the elliptic curve. So just think about it as a constant. It, T is not a number, it's actually a point. So it will a point in a 2D space. So it will have an X coordinate and a Y coordinate, but it's just a constant in our case. And E here in all the presentation today is a non-secret that I will call my private key. This is a number in Bitcoin specific case. It's a 256-bit number. It's to choose a private key it's conceptually simple. You just pick a random number, and that's your private key. It's a little bit more complicated than that because picking random numbers is not that easy, but it's just that. It's just a random number I choose and I keep to myself. I don't tell anyone which number it is. And if I take E, which is this random number, my private key, and I multiply by this constant G, I will get another point. I will define later what those points, how those points exactly work. But I will get another point in a 2D space, which I will call big P, and big P is my public key, right? And the idea is that P will be used to verify the signatures that I produce from E. And the idea here is that uh, given P and given G, so I give you my private key and you know G because it's a constant in the system. The idea is that it's infeasible to factor e out of the thing of this thing, right? And we will see later how this is achieved. Okay. All right. To sign something, so I have E, I have G, I have P. When I'm going to sign something, I pick another random number, which I will call here K, right? And K is it has nothing special other than being a random number that I will promise myself I will only use once. Because if I use this more than once, someone can take my signatures created from the same K, this same random number that I pick myself, and they can calculate back my private key. So this is how, for example, people break used to break some video game consoles security systems because they reuse these random numbers when generating signatures to validate uh, uh, games, right? And this multiplication here will give rise to another point in this 2D space, and with it will have an x coordinate and a y coordinate, and I will be interested only on this uh, x coordinate that I will call r, little r for random, right? So this is the x component of a random point in the system.
Question.
And yes,
So is K E?
no,
So you have to pick two random numbers.
e is a random number that you pick once,
Yes.
and it will be your private key. So you keep it yourself. You will use this many times.
Fine. And K?
K is a random number, another random number,
Okay.
another one that you pick in the beginning of the process of signing something.
So R, little r, is not the x coordinate of P.
No, it's the x coordinate of this number that you are using to create a signature.
Fine. Go on.
So each signature will have a new random R.
Okay.
Fine, and this is important to understand. All right. Given this, I will claim that the following equation is equivalent to this discrete to solving the discrete log problem, right? So let's try to understand what's happening. K is this random number that I am using to build the signature. G is a non-constant. P is this constant. Oh, G is this constant. P is my public key that I can provide to anyone, right? So these are all known things. U and V are arbitrary numbers that I as the signer can choose. But I will show you that there is some logic to choose U and V, right? Okay, so keep this information here because this is kind of given, right? And let's see what we get from this. So, as I said, it's just basic math, right? So it's like summing and multiplication, and you know that you can sum or subtract things on both sides of one equation and to keep everything the same. So it's pretty much the same high school algebra. So there is nothing special. So here I'm taking UG and subtracting on both sides. And here I'm uh, how do I say this in English? I'm putting this together. I'm putting G in evidence.
Yeah,
Don't know
you are
how to.
extracting it, and I think that's fine to say like you're
And
extracting G out of the
out of the
as a common thing between K and U. That's fine. I have a
right.
question though.
Sure.
So everything from the top equation aside from P, actually no, P is public, but the public key. My
Is
question is,
public.
K is also public.
Um, it's not public, but you will see that you don't need K. You just need K for signing, but R will be part of the signature.
Is G public?
Big G, yes,
Yes.
it's a constant in the system, so everyone knows G.
Okay, and U and V, are they public?
N- No, U and V are two things that I want to build when I'm signing, and I want to make it such that someone has to know E to be able to produce U and V in a certain way.
Okay, that's okay.
So just keep with me for now because I'm trying to build a logic to build U and V and be able to prove that someone capable of producing U and V in a certain way has to know E to do so. But I don't want to tell everyone what E is. So I have to do some kind of convoluted math here to hide my private information, which is E, this number, in a way that uh, someone can verify that I know E without revealing E itself.
Yes, 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 yes. I understand.
Um, it's a little bit convoluted,
No,
but
no, no. Okay,
believe
so
me.
let me try to help everybody here. So the goal is to be able to prove something about something that, but you don't know what the something is, right?
Yes,
So you
I
know that I have a phone, but you don't know which phone it is.
yes I as the signer know E, but someone I want to do a signature in such a manner that someone that can verify that I know E without revealing E itself.
Exactly. So you want to be able to prove stuff about the surroundings of a piece of information without
Yes.
revealing what the information actually is.
Yes.
Okay? So go on.
Yes. All right. So I can divide both sides by V, which is just a number. And I have to conclude that P should be equal to this constant here times big G. But P also is equal to my private key times G. So this constant here, which is a scalar, should be equal to E, right? This has to be true. This has to be true. So this whole thing holds together. And the idea here is that I know I am the signer. Remember this. I know E. Okay. I know E. I know K because I choose this random number. So it's easy to just choose U and V in such that this calculation here will equal E because I know E, right? So if I know the secret, it's easy to produce U and V in such that this last equation here will be true. But if I don't know E, I have a problem because if I don't know E, I still know P, which is public information, and I still know G, which is public information as well. So if I'm trying to produce a signature, and if I'm doing this without knowing the secret key, it means that I'm trying to fake someone that knows the secret. I'm trying to produce a counterfeit here, right? So in order to produce this counterfeit, I will have to play with U and V, but it's not obvious what numbers I should put here, U and V, in such a manner that this equation here is also true, right? And there is no other non way other than guessing U and V and testing if this is true, but it's brute forcing U and V. And the idea is that I will make it in such a way on the finite field thing and with the elliptic curve thing that I have to try until the end of the universe lifetime before I get U and V right to be able to produce a valid signature without knowing E. Everyone is good?
I have a question.
Yes.
So I understand that if you don't have E, you are screwed if you use the later version, if you use the last one there. But you
Yes, this
said
one.
that P and G both are public information.
Yes.
Is K public?
It's not public, but it's I know. Remember, here I am the signer, and the signer chooses K.
Yeah, so it's not public.
It's not public, but it's non-information for me.
No, 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 but I'm trying to understand if I'm trying to do bad stuff and trying to be you, how can
Mhm.
I need to guess what are U and V. I have P and I have G because they are public
Yes.
information.
And
And
I want to build U and V given K.
yeah, so
And K will K. I should have said this in the beginning. K produces R, and R is part of the signature. So R will be used to validate the signature later.
wait.
Yeah.
R is going to be used to validate the signature later.
Yes. So
Hmm.
I have to pick K, I have to pick K, and K gives rise to little r. Little r will be part of the signature. So take this. Little r will be part of the signature. It will be used to validate the signature. But I also have to use K to build U and V. So U and V are somehow linked to little r. Do you agree?
Yes.
So I choose K, but I cannot. I have to choose once and fix it.
Yeah, but in terms of somebody trying to mislead people thinking that they are a Jew instead of yourself, they
Yeah.
don't know K.
They don't know K, but
Okay.
they will know R because I will provide as part of the signature. So in some sense, the validator will not know K, but the signer doesn't have K as a as something that he can a lever he can use to fake the thing.
I don't know if I got it. Could you repeat that?
The validator will not have access to K,
Yes.
right?
But they will have
But
access to R.
it will have access to R. So it means that the signer has to fix K to be able to produce U and V, which is valid to be according to this equation, but also valid according to this equation here. There are a lot of things that has to work together.
Yes.
You see?
Yes. So,
So I have
okay.
to fix K.
Yeah, but even that, the person trying to mislead people, they don't know K, and even if
Mhm.
they knew, they would have one equation for two variables,
Yeah.
and that's bad.
Yeah, it sounds easier, right? Instead of having three variables, it will have two variables to guess.
Yeah.
I believe this is what you're trying to say.
Yes.
But this is done in such a way that to produce U and V, it has to guess a gazillion number of U and V combinations so that this equation here is true. But if I do know E, if I'm the faithful signer of the thing, I know E, so I can immediately produce U and V. It's
Yes.
very cheap for me, but it's
Yes.
very expensive for someone trying to forge a signature.
Okay.
So this is the principle of the thing.
Also, remember that K will only be used once per signature, so that makes things harder as well on the attacker side.
Yeah. If K is used more than once, you can prove that it can be it the private key can be recovered from the signatures,
Yeah,
which is
you're giving the attackers more equations. Makes sense.
exactly. And he doesn't need only one more equation, which means if I give an attacker two signatures produced by the same key, he will be able to recover my private key. It's very bad,
Yeah, two variables, two equations. That makes sense.
right? All right. So this is the principle of the thing. I have to choose U and V. This is my goal now, right? I can just randomly pick U and calculate V from this equation, but this is not the thing that I want to do because I want to sign a specific thing. I want to sign a specific message. I'm not signing nothing. I'm committing myself to a specific message. So I want to introduce the message information into U and V, right? So I can do this in many ways, but the standard way of doing this is by defining U and V like so. So Z will be the hash of the message I'm signing. So in my case, I will show you guys. It's kind of a Bitcoin transaction. I will take this information, which is in the transaction, calculate the hash of that, and that will be Z, right? Remember, is the random number that I use to that I can generate from this random number K. So I will also commit R into my calculation here, which makes it way harder to guess from someone trying to fake this thing. And so I know Z in principle. I know the message. I know R because I chose a random number that generates R. I'm trying to compute U and V, and the only thing that I don't know here is S. So I can plug those things into the equation again and build a formula for S. So S, you see, will depend on the message I'm signing, on R, which is built from K, which is one use, one time only use random number, and my private key. So I have to know my private key still to be able to produce S. Everyone good? Because this is it. I will translate these equations into an algorithm now because this is what we are trying to implement in the end. So to sign the thing, it's actually pretty easy. We are given Z, which is the message to sign, actually the hash of the message to sign. I know my private key. I know G, I can produce P, right? I pick a random number. I use this random number to multiply it by G and get little r, which is the x coordinate of R. This is a cheap operation. I use Z, R, E, and K to compute S. I know all the things that I need here. And I will claim that the signature will be a tuple with R, little r, and S. And that's it. Everyone is good?
I have I have a question.
Yeah.
So I couldn't help but notice that we are using for some apparent random reason that we pick the x coordinate of big R.
Mm-hmm.
Why is that? Why couldn't we use the y coordinate, for instance?
Um, I'm not an I'm not a specialist in this, so I can only guess. But I will defer this for the moment you see the shape of the elliptic curve, and maybe you will agree with me that it's that x is something that's unique, but y is something that's kind of not unique in some sense.
Okay. Okay.
So I believe they do so because X will be unique in the curve, but the Y will not. Will not.
Okay,
I'm not sure about this,
that's
right?
fine.
So this algorithm here gives me a way to given a private key that you saw. It's a random number that you keep to yourself and do not reveal to anyone. And given a message, I can produce something that I will call a digital signature, which is just a tuple with this little r and uh, s that I have a formula to produce, right? So the other operation that I want to do is somehow the opposite of signing, which is verifying the signature. So let's see how someone can verify the signature, which is this tuple here provided by the signer, right? So first assumption here, we know this signing algorithm. So we know how the signature was produced, right? I have to know, otherwise I can't verify the thing. Uh, Next, I'm given R and S, and I know a formula for S. So I know that S depends on the message, and the message is the thing that was signed. So I will also consider this message to be public information, or at least the signer gives me the signature and the message that was signed. But I will suppose here that I know what was signed. I know that there is a private key involved, but I don't know the private key because I'm the validator now. I'm not the signer. I know there is a K involved, which is a random number, but I, as the validator, don't know K, but I know R because R is provided in the signature. So good so far? So far, so good?
Yes.
Also, I know that in the process, there, there was numbers U and V produced, and they were produced in such a manner. U is obvious because Z, I know Z and I know S, so I can recover U as the validator. And V, remember, it's R, which I know because it came from the signature, and S because it came from the signature. So I can recover U and V, as you can say. I have all the information that I need to recover U and V. And I know that U and V will be used in this sum here. U will multiply big G and V will multiply big B. So if I put all this together, we will get this last equality here. And remember that I know an equation for S, so I can substitute s here in this little s here for something that I know here, which is the equation. And notice that I will z plus re will cancel z plus re in this calculation here. So sorry, e, which is my private key, will disappear from the calculation. So I, as the validator, will not have access to E in any way. And it will remain K, oops, K times G, which I know that is defined as big R, which I know that gives me little r. So what's the idea here? So you guys understand. I take S and I take the message. So I compute. So I go over this process in the right hand side here, and I will given S and given Z, I will as the validator compute R, and I will compare in the end R that I computed myself with this little r that was provided in the signature. And if they match, I will conclude that this is a valid signature because otherwise I have to, if those two calculations, this number here doesn't match with the one that I computed myself, it means that E does not cancel out here. So the guy that's trying to sign the thing doesn't know the secret key.
Question.
Everyone is good? Yes.
So I kind of understood what you meant by you can verify something about E without knowing E, because
Yeah.
if E is correct, it's gonna cancel out the one with the other, and then you have the thing. But to
Yes.
know little r, you need to know K, right?
To know little r, I have to know K. No, because little r will be given here in the signature.
But you're gonna have to calculate it to know if the little r provided is the one that you are expecting, no?
Yeah, but I can check little r right here in the middle of the calculation. At
Yeah,
least this is my understanding.
yeah, but you don't have K.
You don't have K, yes.
Wait.
But you agree that by doing so, I will end up producing K in the middle of the calculation, or at least one K. I don't know if this is correct or not, but I will produce a K.
Oh, it's because you do know U and V.
Yeah.
So you know U, you know G, you know V, and you know P. You know everything on the other side of the equation.
Yes.
And you know G, so you know K.
Yes.
So if you know
The
K and you know G, you can have little r.
Yeah, I believe you got it. The point is, this is made so that in a way that if the signer knows E, it will cancel out here in this point, and this R will be the same as the one provided by the signer.
Yes.
But if the signer doesn't know E and just faked some R to put there,
You will know.
this will not cancel out because one came from the algorithm and the other came from the UNV that's implied from the signature, and they will not cancel out. And then I will be able to produce an R, let's say an R prime, which will not be the same as this little R that he is providing me.
I see.
You
So
see?
basically, the the correctness is basically the act of being able to cut that thing there
Exactly.
with the other thing there.
Exactly. But to cut this calculation here, I don't have to possess E. I will just translate this into an algorithm, and it will be obvious,
Yes.
right? Because now here you are seeing the calculations that give rise to the things that we have to do, but there will be no E involved in the calculation at the end to
Yeah.
verify the thing.
Okay, so this is basically feeling like the high school problem that everybody
Yes,
here experienced, in which you have a very big like monstrosity of expression, arithmetic expression, and you have some variables that you don't know their values. But the
exactly.
professor stated the problem in a way that when you do the arithmetic manipulations, they will cut, so you don't have to know them anyway. So that's kind of what is happening here, but we are using it to talk about to verify something without knowing the something.
Exactly. And you agree that this can be taught in high school, right?
Sure.
There is nothing special, and the only special thing here is I will have to define what k times g, u times g, what does it mean to multiply a scalar, which are just numbers. Uh, what does it mean to multiply scalar by a point into this elliptic curve thing that you don't know yet what it is?
Isn't
I
that linear
just
algebra? Am I tripping?
it sounds like linear algebra, but it's kind of easier in my way.
Okay, let's go on though.
Yeah. All right. So translating this into an algorithm, we are giving R and S, which is a signature. I'm giving Z as the thing that was signed. I know P because the signer has to provide me his public key in order to verify this thing, right? So the public key is something that I have to use. The signer has to provide to be part of the process. This is why we call it a public key, because it has to be public. It has to be published, right? Otherwise, I cannot verify the thing. So I have those pieces of information. I calculate U and V using the formulas. I calculate big R using the formula. I know G. Remember, it's a constant. It's public information. I know P because the signer gave me P. And I check if R's X coordinate equals R, which is in a signature. And that's it. You will see that there is no E involved here. And that's it. If you understood this, the rest of the thing, I believe it's kind of easy. Kind of easy. Everyone's good?
I think we're fine.
Yeah. And this is pretty much the basics. Uh, Now we are going to the some specifics, right? All right. You Before we go into the elliptic curve thing, let me explain something that you guys asked me in the last session, and I was not able to explain because you asked. Remember when we were verifying a transaction by running a script? At some point in the execution of the thing, there was a public key in the stack, a signature in the stack, and I said to check the signature, you need the signature itself, the public key, and the message that was signed. And there was no message in the stack. And we concluded that this should be some kind of side effect that that specific instruction would provide, right? So it's what does it do, right? Because it has to produce a message to verify. So how it is done? I will show you how it is done to sign, but to verify, you have to do the same thing. So the signer is trying to build this current transaction here, and he has to provide the script sig field. Oops, the script sig field, which contains the signature that relates to these matches to this message. So this is an impossible task. You need a signature to produce something that will be signed. So you can see this is an impossible task.
It's the chicken and
So
egg problem, right?
exactly. So
Okay.
I need the signature to produce the signature. It's not this is cannot be possible. So what is done? The signer will produce this transaction here, and it will erase the script sig field. Then it will take the script pub key field from the previous transaction. That remember, the previous transaction is something that he received and is trying to spend. So I will take the script pub key, which is public information. It's already in the blockchain, and I will copy it into my transaction, into the transaction that I'm signing. And I'm doing this just for the signature production, right? Next, I will add a a a number here, which is called the hash type, which will give you some semantics. I'm not going uh, into this here, but it will is likely to change the semantics of what is being signed, right? So I'm not going to details here about this. And this modified transaction will be double hashed with SHA-256 function. And this final hash is the message, is that Z number that's used to sign and to verify the thing. So you can see it's when I'm verifying, I have the current transaction, and I have access to the previous transaction, so I can rebuild this process and rebuild this Z number, recover this Z number without anyone know telling me any additional information because it's based on public information.
Question.
Yeah,
How did the first transaction worked?
the same.
But there wasn't a previous.
There is always a previous. It's okay because then you can say okay, but that this is some kind of recursion, and I have to have a base case, right?
Pretty much, yeah.
I believe this is what you would say if
Yeah.
I know you.
Yeah, that's pretty
Yeah.
much it.
Okay, so for now, just there are base cases. There is a base case for transactions. They are called coin-based transactions. It's a special kind of transaction, and it will be produced by the miners. All right.
Hmm.
We are going to talk about this when we are going to talk about mining.
Okay, but then the question is, so the first transaction of all, the
Mhm,
first transaction ever put in the blockchain, it was
mhm.
using as the script pub key something that came from the mining.
No, no, because the first ever transaction that is in the first block, the block number 0, which is called the Genesis block, by the way, it has only one transaction in there, and you agree that it cannot point to a previous transaction because there is no previous transaction. But this is not a problem by itself because every block has a Coinbase transaction that doesn't point to a previous transaction. This is not a special thing in the first block.
I don't get it because according to this image, you need the previous transaction, but by construction the first one doesn't have it.
Yeah, but the Coinbase is an edge case which is treated especially in the system.
Okay, so there is a special treatment.
Yes,
Okay,
for
that
this
answers.
specific kind of transaction.
Okay, that answers
The
my question.
Right. A Coinbase transaction is a transaction that has no inputs. It's not right to say it doesn't have inputs, but the data that's put into an input has a different meaning,
Okay.
right? And it has outputs as just like any other transaction,
Okay,
which
yeah.
are the output scripts, remember?
Okay, I have another question though.
Yeah.
So after you need a signature in order to create your signature. That's the problem. So that's why you copied the script pub key from the previous transaction in order to fulfill that requirement, in order to create your signature. And then
Yes.
where does your signature go? Or you just provide to the verifiers?
Yeah, remember, when I'm producing a signature, it means I'm trying to spend something, right?
Yes.
So I will to spend someone something is to say is to provide an unlocking script, and this information is part of the input of a transaction.
Okay, so you're in there it goes your signature, your new signature.
Yes,
Okay.
but you have to understand that I'm not building signatures myself at only signatures. I'm trying to build a transaction.
No, yeah, I think you're collecting the pieces to make a transaction, and one of the pieces is a signature.
Yes, so I want to send you some Bitcoin, right? Me, a Jew, is trying to send Lemos some Bitcoin. So I will do to do so. I have to build a transaction. So I choose a version number. I choose a lock time. I choose by my will. I pick a previous transaction that I believe I control some output there. Remember, it will have a locking script, and part of the unlocking process of that output, of that previous output, is a signature that I have to produce, and I have to produce in this using this convoluted transaction as message using the algorithm that I just showed you guys, and I
Yes.
will put this thing into as part of the input data. And then next, I will produce the outputs. But the output, I don't sign anything to produce outputs. I just produce a locking script, and I use your address to produce the locking script. So it's up to you next to produce a valid signature to be able to spend the funds that I gave you. But you are only doing so when you are going to spend those funds. You got
Okay.
it.
I think I got it.
Right. So the funds, a balance, how many Bitcoin I possess in a given moment in time is something implied by all those previous transaction outputs that I did not spend yet.
Yes.
There is no notion of Bitcoin here. There are only those there are only transactions, and there are outputs that were spent, and there are outputs that were not spent before. And those outputs, those unspent outputs, those are Bitcoins. Those are the tokens in the system,
Oh, I
the
see.
value in the system. You see?
Yeah. So is it fair to say that that if you fold all transactions, you get the state of all the holders of Bitcoin?
Yes.
Okay. So
This
this
is
thing is this is basically
exactly
like a distributed state monad then.
what?
Yeah, because take a look on this.
Yeah,
Yeah.
it's a state. It's the blockchain is the how can I say
Yeah,
the
let me try to put it in better
blockchain.
words. So each transaction is not talking about everybody, right? Because my first
Mm,
instinct was to say the transactions are telling how the state is being mutated. It is changing the state, and it's telling the new state, the current one.
it is.
But that's
It
not,
is.
yeah, but that's not quite true because not all transactions contain the outputs of everybody. So
Yes.
you need to fold them.
Yes.
So it is a scattered state monad, you see?
You see that you have to have the whole history of transactions to be able to produce a balance for everyone in the system, right?
Exactly, exactly.
And that's it. That's it. That's exactly the thing.
Okay, so here's the lesson, folks. This is basically a very weird state monad. That's it. I'm out.
Yeah.
I'm
It's
done.
it's
Got
a
him.
this it's a decentralized state machine. And these are not my words. Do you know Vitalik Buterin, which is the guy that proposed Ethereum? He calls it a distributed state machine. This is how he views it, and he builds his system based on this system, on this view, which is not Satoshi's view, but it's what's happening here. It's a big state. There is a big state machine, and the state is described by the blockchain, which is a record of all transactions once they are validated and put in a specific order, because the order matters.
Yeah, the other matters, but I think it kind of sucks that you need to fold them though. It seems expensive as fuck.
It is expensive as fuck, but you only have to do it once, and then you just here for new blocks and update your state, right? So it's kind of it's pretty. This is actually a name for this, which is initial whatever initial something. That means when you first go into the network, when you launch a node and you connect yourself to the network for the first time, you have to download and verify the whole blockchain
Oh,
before you can do anything.
oh, that sounds
And
expensive.
yeah, I have a node running right by my side here, and it's the current. size of the blockchain is around something around 600 gigabytes to 700 gigabytes, something like that. So it's big, but it's not impossible to download this thing. And it takes a lot of computer power to validate this whole data, because every single transaction in every single block is validated before you claim your copy of the blockchain is indeed valid. And
Actually,
this takes a few days in my machines.
yeah, actually, it
Like
is still a lot. It is still sucks, but it is like validating is not that expensive because if the blocks are already there, you're gonna do that. I don't know that math that you showed us, 4 lines of checking to get the little r and check equality with the r that was given, and you were basically done. But it's very inconvenient that you need to do that all the way through. I imagine they would provide some nodes. They were caching nodes that you could already like jump the blockchain quite a bit, so you don't have to do everything from the ground up.
No, so every node actually does some caching, and actually he builds some databases for its own private use. And one of those databases is actually indexing blocks, so it's faster to retrieve block information. There is another database to index transactions in this in for the node to retrieve them faster.
Yeah,
And there is another database to store transactions that I hear from the individual transactions that I hear from the network, but I did not see them yet in a blockchain. So I also keep those things so I can relay them for other nodes, for example,
I see.
right? Because if I hear a transaction that's not yet in the blockchain, this information has to reach at least one mining node. And if my node's not mining, it's my kind of my duty to relay this to the rest of the network. You agree? It would be considered a fair use, uh, fair behavior in the system, right? I hear something, I validate it because I have all the information to validate new transactions. If I'm a full node here, if this is valid, I relay to my known nodes so that it reaches a mining node and get eventually recorded in the blockchain.
Okay, I have questions about that, but we already getting to our timer, so continue.
No, I believe that this will be a good place to stop, because let me show you. The other part of the thing is I would like to talk about elliptic curves, which need quite some time. Then I have to talk about finite fields, which is another thing which takes some time. And then I have to show you how does elliptic curves work together with finite fields, so that we have you see those scalar point multiplication things, so that this is well defined.
Okay, so we need to go even more deeper to the foundation of the math. That's basically what we need to do.
Yeah, but it takes time. So I will suggest that we stop here and keep taking questions until there are no other questions.
Okay. Do you have any
You have
questions?
any questions?
I don't have any
I
questions
don't have
about
any.
what happened here.
I didn't hear the chat. If you can relate to me.
No,
I
there's
don't have
nothing
any
that.
questions.
Okay, so Nathan and Mars, you guys have questions.
Yeah, I don't have any questions as well.
All right. So you see the actual algorithms to sign and verify are quite simple. It's easy to code this thing actually. The hard thing are, one, to code it in a secure manner without revealing side information that could be used to reveal my private key. in the process of signing and verifying,
Yeah, reverse
right?
engineering is a threat.
Exactly. And this is pretty much the main cause of hacks today, because the math is pretty much bulletproof, but the main weak points are the implementation of the primitives that we use in the system. So multiplying numbers, multiplying big numbers, multiplying numbers by those points. This multiplication reveals signed information. For example, for some for some combination of number and point, I can the actual computations can take more or less time, and I can relate this to specific numbers if
Oh
I know the
wow,
implementation. Yes,
that's
very
unexpected.
it's very wild, because usually those things are open source, so I can inspect code, and I do a lot of experiments to uh, build those correlations. I don't need to know all correlations. I need some correlations to be able to make better guesses when I'm trying to brute force the thing. As you can see, it is still brute force, but if I can find shortcuts because of side information, it it will make it a. I can be able to break the system. And the other point of attack, which is quite common, is the you see that my private key is only it's nothing more than a random number, right?
Yeah,
So I have to generate a random number in the beginning of anything.
which is itself a
And
problem.
yes, because there are safe algorithms to do so, but they need some kind of entropy, right? So our computers produce some entropy using mouse movement and noise and all those kinds of physical process, but this is not perfect. Someone can use, for example, if someone knows that I produced my private key between, I don't know, the January the first 24 and January 31 24. Given this information, it can reverse
Narrow it
engineer
down. Yeah.
algorithm and do educated guesses about the random numbers that could be generated on that specific time range, which is wild. I have no idea how they do this, right? And another way of doing this is by doing physical process yourself. So people actually take some dice and roll dice a lot of times and produce entropy without any specific algorithm. But also you can mess with this thing. And even worse, this private key, there is a standard in Bitcoin to encode the private key information into a set of words, readable words, English words, right? And people think they can just pick some random words from this list and produce a safe private key, but this is not true, right? Because you can imagine, Lemos, there are some words people will going are going to say, I will pick this, and I will pick that, and I will pick this other word, and I will form a phrase. But you can imagine, given a finite number of words, I can uh, do I can I am a human as well. I can build all the or at least a lot of combinations that make sense as phrases in English, not nonsense phrases, like real phrases from this table. And then I can use this to guess, just like guessing
Yeah, it's
passwords.
even worse.
Word.
Are people really doing that? Do people really believe that?
Come on, people still use 1, 2, 3, 4, 5 as passwords.
That's fair.
For real. And for critical systems.
Yeah, but we are talking about like a
More
millennial
like a
problem of
millennial problem.
random numbers, and people are using phrases that make sense in English language. Like, what are you guys
Yeah,
doing, bro?
yeah, people do all kind of dumb stuff. But you can see those are the 2 points of attack. Once you know, and of course you can imagine why not I start guessing private keys, because if I have a private key and if I have a copy of the blockchain, I can scan the blockchain and see if this private key can unlock some funds there. This is possible. This is pretty easy actually to do, right? So the this is not feasible because the number of private keys is so huge that it's the number of private keys is comparable to the number of atoms in the whole observable universe. So when you're picking a private key, it's equivalent somehow to picking an atom on the universe and claiming this is your atom.
Yeah, I think that's
So
pretty hard to guess.
yes, it's pretty hard to guess because there are a lot more, way, a humongous more unpicked private keys than picked private keys,
Yeah.
right? So it's like hell to guess. So in practice, that thing doesn't happen.
Okay. So I think that was great. So do you have any more questions so we can finish the recording?
Not from my side. Maybe
I
you
also don't
guys.
have questions. I have feedback though. I'm gonna say that shortly.
Yeah, yeah, sure. I expect this.
Okay,
So I
so
think we
okay, so nothing. I'm gonna stop the recording now.